My name is Owen McGarry, and I conducted an experiment to assess the efficacy of various fabrics in blocking ultraviolet light. Here's what I learned, not only about fabrics in ultraviolet light, but about the process of thoroughly conducting an experiment that reveals data relevant to important scientific topics. Ultraviolet radiation is the leading cause of skin cancer. Throughout history, fabrics have been used to protect the skin from the sun's harsh ultraviolet rays, but only recently has research revealed that certain fabrics are more capable of blocking these rays than others. Ultraviolet rays can be classified into three types: UVA, UVB, and UVC. UVA radiation has a wavelength extending from 320 nanometers to 400 nanometers. UVB radiation has a wavelength extending from 290 nanometers to 320 nanometers. And UVC has a wavelength extending from 100 nanometers to 290 nanometers. UVA and UVB are more relevant because UVC is blocked almost entirely by the ozone layer. The most prominent source of ultraviolet emission is the sun. Ultraviolet radiation has been found to cause cancer and immunosuppression when skin is exposed to it in large doses. This has resulted in an emphasis on ultraviolet deterring fabrics in clothing. In addition to clothing, there are multiple protective agents against ultraviolet radiation. The more prominent of these are the ozone layer and sunscreen. The ozone layer filters large amounts of ultraviolet radiation released by the sun, especially the carcinogenic UVC and UVB radiations. If there would be a 10% depletion in the ozone layer, it is projected that there would be 300,000 additional cancer cases. Sunscreen also protects from ultraviolet radiation. It takes 20 minutes for the sun to burn completely unprotected skin, but the application of SPF 15 sunscreen increases its duration 15 times. Scientists recommend that SPF 30 or above is used for optimal protection, and that reapplication of sunscreen occurs every 2 hours. Skin cancer and immunosuppression are two real dangers that have resulted in countless dollars of research. Cotton and linen are two fabrics that observe frequent usage in the Middle East, which is a desert climate. Based on this historical data, it can be hypothesized that if cotton or linen are used, then the most ultraviolet radiation will be blocked. The purpose of this experiment is to ascertain which fabrics are most capable of blocking ultraviolet radiation. The materials that were used in this experiment are as follows: 1 LED plant grow light, 1 bag of ultraviolet glow beads containing 1,000 beads, 11 4-inch embroidery hoops, 11 fabric samples cut down to 1/4 of a yard. These samples are of rayon, nylon, cotton, linen, satin, pleather, plastic leather, jute, polypropylene, denim, polyester, and wool acrylic. 12 3-inch bowls, 1 tray, a pair of scissors, a roll of measuring tape, a roll of masking tape, a Sharpie, and a stopwatch. The procedure for this experiment was as follows. The materials were gathered. The tape and marker were used to label each bowl to a corresponding fabric. All 12 bowls were placed on a tray. 20 ultraviolet beads were added to each bowl. Each fabric was placed in its own embroidery hoop. Then the excess fabric was cut off. The ultraviolet lamp was hung so that there was 1 inch of space between the lamp and the rim of a bowl. The bowls were divided into the 3 testing groups so that equal amount of exposure to ultraviolet light would be ensured. The bowls were covered with their corresponding fabrics. Group 1 was then placed underneath the ultraviolet lamp. The lamp was turned on and the bowls were exposed to ultraviolet light for 5 minutes. The bowls were then removed from the lamp and the fabrics were taken off. An observation was recorded, and then A subsequent observation occurred every 5 minutes until 20 minutes had passed. This process was repeated for the next 2 testing groups. This was the procedure for the experiment. Here are the tables and images collected during testing. In Trial 1, polypropylene was the most successful fabric at blocking ultraviolet light. 0 minutes post-exposure, the beads were barely lit. This implies that extremely little ultraviolet radiation reached the beads through the fabric. Denim was the second most successful at blocking ultraviolet light. The beads were slightly brighter than that of polypropylenes at 0 minutes post-exposure, but fading quickly occurred between the first observation and 10 minutes post-exposure. The last 2 samples were not as successful. Polypropylene and denim were very dark at the beginning of testing, but polyester and wool acrylic were both bright. Polyester saw more fading than wool acrylic, which implies that it was the third most successful sample in the trial. There was less radiation in the beads to fade, and so polyester was superior to wool acrylic. Wool acrylic was the least successful in the trial. In Trial 2, nylon was the most effective fabric at blocking ultraviolet light. 5 minutes post-exposure, the beads were completely dim and faded. This occurred at a much faster rate than in the other samples, implying that the beads in nylon's sample were exposed to less ultraviolet light and that nylon was better at blocking. The second most successful fabric sample was satin. Aside from nylon, it was the only fabric to have a completely dark set of beads at 20 minutes. The third and fourth most successful samples in the trial were indistinguishable based on the similar trends that these fabrics displayed. Linen and rayon showed the same pattern of fading and brightness throughout the experiment, so it cannot be determined which was the superior fabric at blocking ultraviolet light without more sophisticated tools. Leather was the most successful sample in Trial 3. This sample was completely dark 0 minutes post-exposure. This means that little or no ultraviolet light reached the beads through the fabric. The second most successful fabric in this trial was jute. Jute had a relatively dim sample at 0 minutes, but it was still much brighter than leather. There was a great deal of fading in the sample, and it was completely dark at 20 minutes. The only other fabric in this group was cotton, which was not dark at 20 minutes. The last sample was the control, and this had no fabric covering it. It also was not dark at 20 minutes, and was the brightest of the group. The 3 most indisputably successful fabrics were polypropylene, nylon, and leather. According to the table, the beads underneath these 3 were either completely dim or almost completely dim at 0 minutes into experimentation. That means that the fabrics were able to shelter the beads almost completely from the incoming ultraviolet radiation. The fabric samples that were least effective were wool acrylic, rayon, linen, and cotton. According to the tables, these samples were the only ones to not be completely dim by 20 minutes. This shows how the other fabrics were more capable of blocking ultraviolet radiation than these samples. This data refutes the hypothesis. The hypothesis stated that cotton and linen would have the most success based on the historical information that these fabrics were the most commonly worn in the Middle East, a region with intense sun exposure. The data revealed that cotton and linen were among the least successful of the fabrics tested. Accessibility and not practicality may account for linen and cotton being used so frequently in the Middle East. Some applications for this experiment include maximum protection when traveling outdoors in areas of heavy sunlight. An example of a sun-proof outfit may be nylon shirt and pants paired with a leather jacket underneath a polypropylene tent. Aside from maximizing sun protection in clothing, Other applications for this data include optimal materials for tents and other forms of shelters. The experiment conducted to assess the efficacy of various fabrics in blocking ultraviolet radiation was not perfect. There were multiple flaws in the experiment. The beads used in the experiment provided extremely imprecise data. Also, the effect of the ultraviolet light on the beads was only visible in complete darkness, which made it very difficult to work and make observations. Also, the size of the ultraviolet lamp became problematic. There was only room for 4 bowls to be tested at a time, meaning that one all-fabric encompassing trial could not be conducted. If given the opportunity to redo this project, there are many changes that are necessary to make. First, the ultraviolet beads would be replaced with a more sophisticated and precise measure of ultraviolet radiation. Then, a larger lamp would be used in place of the smaller one to allow each sample to be tested in one trial. These are the potential improvements to be made based on the flaws encountered in the experiment.